In this video, our focus of attention will be on Schmid's law. So the spelling is okay. This is more because last lecture we were discussing about the resolved shear stress. Now, first we will see what is critical resolved shear stress. Critical resolved shear stress. Okay. First, let us see what is critical resolved shear stress. Then we will move on. So, resolved shear stress. In the last lecture, we have seen that the formula is sigma cos phi n phi d. Okay. So if you plot between two RSS, okay, two RSS and sigma, you can plot a linear plot here. You can see that four, that means two critical resolved shear stress, and this is corresponds to sigma y, and this slope will give you cos phi n cos phi d. Okay, so this is the Schmidt factor. Okay, this is the Schmidt factor. So we can see that critical shear stress is the shear stress corresponding to the yield stress. That means when the material starts yielding. So that is sigma y cos phi n cos phi d. And this cos phi n phi d is the Schmidt factor. And this depends upon, okay, this depends upon the orientation, depends upon the orientation of stress axis, okay, orientation of stress axis with respect to slip system, okay, with respect to slip system. Okay. So the value of RSS, okay, the value of resolved shear stress at the point of yielding, at the point of yielding is called, the point of yielding is called critical resolved shear stress, is called critical resolved shear stress or tau CRS. That is the, I write it down, critical resolved shear stress. Okay, that is tau CRS. So this tau CRS and this sigma y both are material properties. Okay, so these are material property. It does not depend upon the orientation. So now the question is, if we change, okay, so we will ask a question, that is, if we change cos phi n cos phi d by changing the orientation, okay, changing the orientation of stress axis, okay, stress axis with the respect to slip system, with the respect to slip system, what happens to the equality? To equality. That means we have written that tau CRSS is equal to sigma y cos phi n cos phi d. So that means if you are changing this cos phi n, we can freely change that phi n and phi d. We can change this by changing the orientation of stress axis with respect to the stress system. So what will change? So the three possibilities: two CRSs can change, and sigma y remains constant. Y remains when you change the orientation. The second option is sigma y changes and tau CRSS remains constant. Third one is both changes. Yeah. What may be the answer? The answer to this one is It was found by Schmidt. He performed experiment to establish which option is right. He found out that sigma y changes and this tau CRSS remains constant. This was the answer Schmidt found. Okay, and this became the famous Schmidt's law. That means this critical resolved shear stress is independent is independent of the orientation. It is independent of the orientation of stress axis, orientation of stress axis with respect to slip system. Okay, that is a constant. Okay, so that means sigma y changes. We have seen that that is a material property. So that is why we come to this concept that is anisotropy of yield stress. What do you mean by yield anisotropy? That means the material property varies in different direction. You can see that in different orientation, the sigma y will be different. So this is equal to sigma y cos phi and cos phi d. That is sigma y is equal to tau CRSS by cos phi n cos phi d. Okay, so that means this yield stress sigma y depends upon this orientation. So that means this yield stress of a single crystal of a single crystal depends upon the orientation of the stress axis. Orientation of the stress